Great. So up till now, we've been talking about things called discrete random variables, but it's possible that you have a random variable that could take on, any values in an interval, real numbers. For instance, if you're um, asking for the lifetime of a light bulb, it makes sense that it could last 10.254 months. And so it really could take decimal values. In that case, it doesn't make sense to try to sum up the probabilities. Um, Instead, we give a probability density function. So the probability really of any particular value is zero. Really, what's the chance that my light bulb lasts exactly 10.254 months and no, not 10.2541 months or that many months plus a second, right? It seems like it should be zero, and it is. But we can give a likelihood function, which is called the probability density function, and then if we have that function, the probability that our random variable takes values between two particular numbers is given by the integral, the area under that probability density function. Here's an example. The cumulative density function is very similarly defined to that for a discrete random variable. It's going to be the probability that capital X is that our random variable takes value less than or equal to X. And this is given by an integral of the probability density function starting all the way at minus infinity and going up until the value that you're interested in evaluating at, in this case 10. And notice something kind of interesting here. F of 10 is a particular number, right? It's this number. But f of x is a function of x. And if we were to replace 10 with x so that we have the definition of f of x here, what we would see is that if we were to take the derivative of this quantity with 10 replaced by x, we would be able to use the fundamental theorem of calculus to show that when you take the derivative of capital F, you get lowercase f. Kind of makes some sense, but there's a nice connection between the ideas of calculus and the ideas of continuous probability. Okay, you might not be that excited about the opportunity to practice your calculus skills by integrating functions like this, but you don't actually have to either. In Python, there's a SciPy library, scientific Python library, that contains a lot of distributions in the stats sublibrary. And one of the distributions is called the expon distribution, the exponential distribution. So, and an exponential distribution is determined by its scale, by the scale parameter lambda. And if you know lambda, then you can plug in for lambda here and get the PDF of your exponential distribution. And in this example up above, if you compare this function with this function here, you see that lambda is 20. Okay, you can access the height of the PDF at x equals 10. You can plug 10 into this little function here by first importing from SciPy stats the exponential class of functions, and then taking exponential.pdf, you have to give it the x value and the scale, and it will report back the probability. Okay, I guess actually this isn't quite a probability. This is the height of the probability density function at x equals 10. If you're interested in the CDF, which is really measuring probabilities, we could calculate the expon CDF at x equals 10, the scale equals 20, and that gives us 0.393, and that's the probability that a scale 20 exponential distribution takes value less than or equal to 10, and that's exactly this calculation that we did up here without actually having to compute the integral using calculus. Okay. So that tells you how to compute the probability that a value is less than or equal to 10. If you wanted the probability that a value was between, say, 20 and 10, you would do it this way. You'd calculate all the probability that your variable is less than or equal to 20, and you'd subtract off the probability to the left of 10, and that will give you the correct answer that that the probability is that the random variable is between 10 and 20. Okay, so you can use this difference of CDFs in order to compute some probabilities. And then you can also access the mean and the variance of the exponential distribution with particular scale in this way. So here we're going to set a variable f30 to be the CDF value for f30 in our light bulb example. So we just want expon CDF. We want x equal to 30, and we want the scale equal to 20. And it's just a bit higher than 3/4 as expected. And if we wanted to interpret this value of f30, we could write something like this. This means that, that there is a, 77.7% chance that the bulb lasts less than 30, what are the units? Months? Months, yeah. There we go. All right, you can compute the expected value of a continuous distribution too. The expected value is just the integral, not of the PDF, but of x times the PDF. And you can also compute the variance, which is the integral over all possible values of the difference between x and the expected value squared times the PDF. Right. So let's compute that for the light bulb. If x is distributed with the exponential distribution, the scale equals 20. So we want the expected value of the exponential distribution with mean scale equals 20. Yep, it's equal to 20. And in general, that's always true for an exponential distribution. The mean of the exponential distribution is equal to its scale. And let's calculate the variance using the var method. Again, for scale equal 20. And here it's 400. And the digits, yes, do sum to 4. In general, the variance of the expected value, the variance of the exponential distribution with scale equals 20, it should be the square of 20, and more generally, it should be the square of the scale. So the standard deviation for an exponential distribution is equal to the scale. Mm-hmm. Of course, you can do things with the normal distribution as well. There, we need to talk about the location. That's the center of the distribution. And the scale here, in this case, is the standard deviation. So that's the normal distribution. And there's this related idea of the T distribution, the student T distribution. Remember that if you take many um, observations and you average them, you usually get a normal distribution if your number of observations is high enough, and that's the kind of content of the central limit theorem. But what if you didn't have enough observations? What if it wasn't very high? Then what distribution would you get then? And the answer is the student T distribution. And so here in this calculation, we compute the probability that you would get a value between 30 and 50 if you took a sample average of 9 observations among a population that has mean 40 and standard deviation 30. So the standard deviation of the sample average would be the standard deviation of the original population divided by the square root of the population size, and that's 10. And that is the standard deviation for the T distribution. So that's the scale here, 10. The location is the mean value, which is mean 40, sorry, right here. And the degrees of freedom is one less than the number of observations. And then you go ahead and you calculate. In this case, we wanted the probability that your sample average is between 30 and 50. So take the probability that you get a value 50 or less, and subtract off the probability that you get a value 30 or less, and that leaves you with the probability that you get a value between 30 and 50. And that turns out to be about 65%, which is pretty darn close to the number predicted by the normal distribution. Here we're talking about the probability that you're within one standard deviation of the mean, and we know that that should be just about 68% for a normal distribution, and it is. So we're just a little bit different. That's why we use a student T distribution in some situations rather than a normal distribution, particularly in the situations where we have a small number of sample averages. We often use the student T distribution as opposed to the normal distribution. All right, thanks a lot for listening to me go through the Day 30 lecture notes. In the next class, we'll have a review of some of the material that we've been talking about in order to get us ready for the term test that's coming up, and our midterm test will be on day 32. Okay, see you soon.